Welcome everybody once again. So we are studying our moment distribution method. This is our sixth class, and in the previous classes we saw the basics of moment distribution method, how to find the relative stiffness, how to find the absolute stiffness, how to find the distribution factors. We saw how to solve a continuous beams using moment distribution method. So today we are going to see another type of problem. See, the speciality of this problem is the joint B consists of three members, BA, BC and BD. In the previous problems of continuous beams, analyzing the continuous beams, we had only two members meeting at a joint. But here we have three members meeting at a joint. In such cases, how will we analyze the beams? Okay, so let us see. See, our given problem is a continuous beam ABC is supported on an elastic column BD. So you have a column, elastic column BD. ABC is a beam. A is fixed support, D is simple support. And this ABC continuous beam is resting on an elastic column BD, where D has fixed support and is loaded as shown in the figure. So in the span AB, we have a 10 kilonewton concentrated load acting at a distance of 2 meter from A. In the span BC, we have a UDL of 2 kilonewton per meter. And in the span BD, we do not have any external loads. Treating joint B as rigid, and analyze the frame and plot the bending moment diagram and sketch the deflected shape of the structure. That is your problem. Okay. So now, see, as usual, our first step is finding the fixed end moments. So we know the formula for finding the fixed end moments if it is an UDL, right? So first of all, fixed end moments for the span AB. So for the span AB, we have two fixed end moments at end A and at end B. So MF AB is equal to, see, we have a concentrated load acting at a distance of 2 meters from A. So formula is the left. See, we know when we are considering, we will find the fixed end moments by assuming all the supports as fixed. So if we are considering the span AB, we have a 10 kilonewton load acting at a distance of 2 meter from A. So when we are taking a section, we know, see, when we have fixed supports, we will have a hogging moment. That means we have negative moments, which means when we take anywhere the section, hogging moment means the left anti-clockwise is hogging and right clockwise is hogging. That is why in the left it is minus and in the right it is positive. So M of AB we have a negative sign, M of BA we have a positive sign. So the formula is minus WAB square. So this is taken as A, this distance is taken as B. So minus M of AB is equal to minus WAB square by L square. We get minus 10 into 2 into 3 square divided by 5 square. We get minus 7.2 kilonewton meter. Similarly, M of BA will be equal to positive. Right side it will be positive. Right support we will have a positive moment. Then only we will get a hogging moment there. So WA square B by L square, it is minus 10 into 2 square by 2 square multiplied by 3 by 5 square. The value is 4.8 kilonewton meter. Now we will move on to our second span. So the second span is BC, right? So AB is over. Next is BC. And in BC, we have a 2 kilonewton per meter concentrated load. The span length is 3 meter. So we have two moments, two fixed end moments for the span BC, one at end B and another at end C. So here for the span BC, this is B and this is C. For finding the fixed end moment, we will assume the supports are fixed we have a UDL of 2 kilonewton per meter for a span length, throughout the span length, and our span length is 3 meter. So what we have is, our formula is, in the left it is minus WL square by 12, and at the right support we have plus WL square by 12, anti-clockwise and clockwise. Anti-clockwise at the left support, clockwise at the right support. So substituting minus WL square by 12, we get minus 1.5 kilonewton meter, and the fixed end moment at a C is M of CB is equal to WL square by 12, that is equal to 2 into 3 square by 12, it is 15 kilonewton meter. Now we will move on to the next span. Our next span is BD. So BD do not have any external loads. That means fixed end moment at B and D is equal to 0. M of BD and M of DB is equal to 0. So we have written here M of BD and M of DB is equal to 0. So first step is over. We will move on to our second step, that is finding the distribution factors. So now you should be careful while finding the distribution factors. So we have, see, previous problems we had only 2 members, here we have 3 members. So distribution factors, we know when the far end is fixed, our relative stiffness is equal to I by L, and when the far end is hinged or simply supported, the relative stiffness is equal to 3 by 4 into I by L. Sorry, 3 by 4 into I by L. So here we have only one joint where more than one member meets. So at A we have only one member. So our distribution factor will be equal to 1 here. At C we have only one member. So distribution factor will be equal to 1. At D we have only one member. So distribution factor will be equal to 1 for this member at joint D. But at joint B we have 3 members. So we have to find how the moments are distributed between these 3 moments. So what is the distribution factor between the members BA, BD and BC at joint B? Okay. Now because the total moments at B will be equal to 0. Total moment at B will be equal to 0. So how these moments are distributed? Now we will find the distribution factor. Okay, so at joint B, see, when you are considering BA, the far end is fixed, so our distribution factor is I by L. I is taken as 2I. L is 5. When you are considering BC, the distribution factor is, the far end is hinged, so distribution factor, so the relative stiffness, not the distribution factor, relative stiffness, here it is I by L. Here for BC, the relative stiffness is equal to 3 by 4 I by L. I is I, L is 3. For the span BD, the relative stiffness is equal to, the far end is fixed, so it is I by L. So it is I by 3. Okay. So now we will write. So at joint B we have 3 members, right? At joint B we have 3 members. It is fixed, it is hinged, and at D also it is fixed. Here it is 2I, I, 5 meter, 3 meter and 3 meter. Okay. So the members are AB, sorry, we have to write it as BA. BA, BC and BD. So when you are taking BA, the far end is fixed. So the relative stiffness is I by L. For AB, I is given as 2I. So it is 2I by 5. For the span BC, the far end is hinged or simple support. So relative stiffness is 3 by 4 into I by L. So 3 by 4 into I is I here, L is 3. So it is I by 4. For BD, the far end is fixed. Far end, that is D is fixed. So relative stiffness is I by L, I by 3. So here it is I by 4. You can cancel 3 and 3. So now what we get is the sum. You add 2i by 5 plus I by 4 plus I by 3. We get 59i by 60. So distribution factor is k by sigma k. So 2i by 5 divided by 59i by 60. We get 0.406. Similarly, k by sigma k, that is I by 4 divided by 59 and I by 60, we get 0.254. Again, I by 3 divided by 59, I by 60, we get 0.340. So this is our distribution factor. See, next step is different from the previous problems. We have to be very careful. So third step is moment distribution. We will consider the joins. We have 4 joins, right? Fixed and hinged. A, B, C and D. So we have written the joins A, B, C and D. Now we will write the members. At A we have the member AB. At B we have 3 members BA, BC and BD. So at B we have BD, BA and BC. See, the reason is this is the span AB, AB, BA, AB, BA. See here, while you are writing at C you have CB, right? So these both comes together because this is one span BC. This span is AB. Now at D we have DB. DB. So this BD and DB. So the sharing of moments is between A and B, between B and C, and between B and D. B and D. So you should be very careful. Now we will write the distribution factors. So our distribution factors. Okay, we will write the distribution factor. So we have found for BA. For BA the distribution factor is 0.406. For BD the distribution factor is 0.340. For BC the distribution factor is 0.254. Okay, now we will draw the lines. That is, see how will we draw the lines? AB is a beam, right? So the sharing of moments is between A and B. Between A and B. So it is between A and B. So these both comes together. So we will put a line here. BC and CB comes together. So we will separate this. So AB, BC and BD. Okay. So we will separate it. So AB, BC and BD. Now we have one end as symbol support. C is a symbol support. So first of all we will write the fixed end moments. So what is our fixed end moments? Now we will write the fixed end moments. We have determined our fixed end moments in the first step. That is M of AB is minus 7.2 plus 4.8 minus 1.5, 15, 0, 0. So M of AB is minus 7.2 kilonewton meter. It is minus 7.2 For BA, it is plus 4.8. Okay, plus 4.8. For BC, it is minus 1.5. And CB, it is plus 1.5. So for BC, it is minus 1.5. And for CB, it is plus 1.5. For DB, between B and D, in the span BD, we do not have any external loads. So the fixed end moment is 0. Now, see, we have at least one far end as symbol support. So in the next step, we have to balance and carry. Balance and carry the moment from this fixed symbol support, that is from C to B. We have to carry the moment from C to B. Okay, first of all, we will balance C and carry it to B. So, balance and carry C to B. So, how will we balance this C? It is plus 1.50. So, balancing we get minus 1.50. And carrying it to B, half of this, because B is an intermediate support, that will be considered as fixed support. So, half of this 1.50 will be carried to the nearer support. So, minus 1.50 divided by 2, it is minus 0.75. So, this step is over. Now, we will write our initial moments. So, now what is the initial moments? How will we write the initial moments? Okay, so at AB, A is fixed support. So, our initial moment is minus 7.20. Here our initial moment is plus 4.80. Initial moment is 0. Now, minus 1.5 minus 0.75, we get minus 2.25. Here it is 0 and 0. Okay. Now we will go for balancing. Next step is balance. So while balancing, here it is already fixed support. A is fixed support. So it will carry the moments. So no balancing. At B, plus 4.80 minus 2.25 multiplied by 0.406. That is plus 4.8 minus 2.25 multiplied by 0.406 plus 4.80 minus 2.25 multiplied by the distribution factor 0.406. We get plus 1.03. So balancing, it is minus 1.03. Again, the distribution factor, again the moments, that is plus 4.8 minus 2.25 multiplied by 0.340. 0.340, we get plus 0.87. So balancing, we get minus 0.87. Again, plus 4.80 minus 2.25 multiplied by 0.254, we get plus 0.65. So balancing, it is minus 0.65. Okay. Now, we don't have anything. Now, next step is carryover. So, we will carry, since this is fixed, the carryover is between A and B, between B and C, and between B and D. So, when you are carrying from A to B, See, A is fixed support. So there is no carrying from A. But from B, half is carried to A. From B, half is carried to A. Now you take BC, far end is hinged. So no carryover. C, already it is balanced and carried. Now between B and D, from D it is fixed support, so no carryover. From B, half is carried to D. So from B, half is carried to D here. Okay, so minus 1.03 divided by 2 we get minus 0.52. Minus 0.87 divided by 2 we get minus 0.44. Remaining place there is no moment. There is no carryover of moments. Okay, only from, see, when you see the diagram you will understand. The moment is carried from B to A. Half of B in AB, half of B is carried to A. Here, no. C is already balanced and it has been carried to B. So from BD, half of B is carried to D. D is fixed support, so that will not give it to the next end. It will carry its own. So there is no transfer from D to B. Transferring is from B to D. Here there is no transfer from A to B. Transferring is from B to A. Okay, so you see, next step will be balancing, but there is nothing to balance. See, at B we do not have any moments for balancing. So we will stop here. This is our final moments. Final end moments. Okay. So our final end moments are, so we have to start, see here we have to put a double line actually. So we have to start from this. So minus 7.20 minus 0.52, we get minus 7.72. Plus 4.80 minus 1.03, we get plus 3.77. 0 minus 0.87, we get minus 0.87. Minus 2.25 minus 0.65, we get minus 2.90. 0, minus 0.44, we get minus 0.44. See, you add all these things, plus 3.77 minus 0.87 minus 2.90, totally you get 0. You add these, you will get 0. Okay. So now we will, our last step. Next step is writing the fixed and final end moments. So step 4. Our final end moments. Our final end moments are MAB, MBA, MBC, MCB, MBD and MDB. So MAB is minus 7.72 kilonewton meter. MBA is plus 3.77 kilonewton meter. Next, this is BD, right? For BD, 0.87. Minus 0.87. For BD, it is minus 0.87 kilonewton meter. This is between BC. So minus 2.9 kilonewton meter. MCB is 0 and MDB is minus 0.44 kilonewton meter. Now we will write the Step 5, in order to draw the bending moment diagram, we have to find the initial beam moments. That is simple beam moments. Simple beam moments due to the external loadings. So, simple beam moments for the span AB. For span AB, see, we know our span AB is like this. So, simple beam moments, we will be finding the moments by considering all these supports as a simple support. We have a 10 kilonewton load acting at a distance of 2 meter from A, and this is 3 meter. Therefore, our M max is equal to WAB by L. WAB by L. So, W is 10. A is 2, B is 3 divided by 5. We get M max as 12 kilonewton meter. Similarly, for the span BC, we have an UDL of 2 kilonewton per meter for a distance of 3 meter. 2 kilonewton per meter for a distance of 3 meter. So, M max is equal to WL square by 8. WL square by 8. So, 2 into 3 square divided by 8, we get 2.25 kilonewton meter. Now, for the span BD, there is no external loadings. So, we don't have any simple beam moments. Now, we will draw the bending moment diagram. Okay, so how will we draw the bending moment diagram? Okay, so A, C, B. This is D. So, by drawing the simple beam moment diagram, we have the values as 12 kilonewton and 2.25 kilonewton meter. 12 kilonewton meter and 2.25 kilonewton meter. So, in AB, the maximum moment is where the concentrated load acts. So, here, right? So, this is 12 kilonewton meter, and in BC, because of this UDL, we will have a parabolic shape, and the intensity is 2.25 kilonewton meter. Now, we will draw the final end moments due to fixed supports. So, that we have determined our final end moments as minus 7.72 plus 3.57 for AB and BA. Minus 7.72 and plus 3.77. So, here at A, when you are considering AB, see, when you are considering the span AB, the values are minus 7.72. That means anti-clockwise. See, draw anti-clockwise, it is pointing upwards. So, we will write here, it is pointing upwards. Value is 7.72. Okay. So, 7.72 kilonewton meter. For BA, MBA is plus 3.77 kilonewton meter. So, plus means it is clockwise, right? So, you draw the clockwise pointing upwards. So, it is plus 3.77 comes somewhere here. 3.77 kilonewton meter. So, how will we draw this? Okay, that means this is positive, this is negative. From this to this point, you have a hogging moment, and from this to this you have a sagging. Then again from this to this you have a hogging. Then for the span BC, see when you are considering the span BC, the moments, what is the value for final end moments? Final end moments are, for BC it is minus 2.90 and for CB it is 0. So for BC it is minus 2.90, that means anti-clockwise, pointing upwards, right? So for BC it is minus 2.90. So minus 2.90 comes somewhere here, right? So 2.90 kilonewton meter, and at C it is 0. So there is a drop here. See, that is the meaning of that. From 3.77 there is a drop here. Then at C it is 0. That means this portion is negative. We have a hogging, and from this to this, from this point to this point, we have a sagging bending moment, positive bending. Now, for the span BD, there is no external loads, and our final end moments are for BD. D is fixed support, right? So there will be some moment at D. So the values are minus 0.87 at B, and at D it is minus 0.44. Both are minus, both are anti-clockwise. So when you are drawing the beam moment, this bending moment diagram, since both are anti-clockwise, see BD is like this, right? Okay. So this is B and this is D. So at B it is anti-clockwise. At B, that is BD is minus 0.87. Minus 0.87, it is anti-clockwise. So from outside you draw an anti-clockwise. It is facing towards the right. See, that means minus 0.87 comes here. Somewhere here. 0.87. At D, that is MDB is equal to minus 0.44. Again anti-clockwise. Draw an anti-clockwise. It is facing towards the left. The value is minus 0.44. So the value is 0.44. It is 0.44 kilonewton meter. So how will we draw the moment here? From this to it is a straight line, okay? Draw it as a, see, I'm not able to draw it as a straight line. Trying, but okay. Right? So this means here you have a negative bending moment. In here you have a negative bending moment. So how will you draw the deflection diagram? See here, this is sagging and this is hogging. So you can consider this sagging or hogging from which side you view it. So listen, so from this to this, we will draw the deflection diagram now. So while drawing the deflection diagram, from this point to this point, here there is a point of contraflexion. Now we have another point of contraflexion at this point. We have another point of contraflexion, that is from changing its sign. See, negative to positive, positive to negative, negative to positive. Here it is 0. So how will you draw the deflection here? This is hogging, right? So it is like this. Next it is sagging. Next again hogging. Next again pure sagging. See, in this portion, if it is a sagging, it will be like this. Since it is hogging, it is like this, right? So I have marked it this way. Now for the span BD, we will start from D. So here there is a negative moment in this direction. So we have a point of contraflexion here. So here it is hogging, and here also it is hogging. So this is your deflection diagram. Okay. So I will give you one problem for practice. I will give you the problem and you please try to solve that problem. So your problem is a continuous beam. I will draw you the diagram. Okay. Try to solve this problem and see whether you are getting the answer. You have a span A, B, C, D is fixed, C is fixed. Here it is hinged support E, 3 meter length, AD is 3 meter length, BE is 3 meter length. You have a 12 kilonewton concentrated load and another 12 kilonewton concentrated load at a distance of 1 meter from A, at a distance of 1 meter from B. So this is 1 meter, so totally 3 meters. For BC, it is 4 meter, the span length is 4 meter. We have a UDL of 4 kilonewton per meter. And the moment of inertia I is constant everywhere. So I is constant everywhere, is same throughout the beam. Okay. So now I will give you the bending moments diagram. See whether you are getting the answer. Okay. Your final bending moment is okay. Anyway, I will give you draw the bending moment diagram. Two 2.24, 4.47, because you have two concentrated load, right? So it is 12, 12, it is 8. When drawing the fixed end moments, it is 4.47, 6.80, sorry, 8.27, 6.80. So fixed support, right? So you get 4.60. Here it is 1.47 and this is hinged. So here you get 0. It is 0 here, right? Straight line meeting at 0. So that's all for today. Thank you.